Good morning and good afternoon, everyone. On behalf of the World Council of Civil Engineers, it is my pleasure to welcome you to today's webinar titled Model Seismic Code for Latin America and the Caribbean. We sincerely appreciate your participation. Before we begin, I would like to mention that you are welcome to submit your questions throughout the session using the chat of the Q&A box. Additionally, we'll be sharing a short survey in the chat. We will greatly appreciate your collaboration in completing it, as your feedback is essential for improving our future events. Participants who complete the survey will receive a certificate of participation. And now, it's my honor to introduce today's speaker, Dr. Miguel Cruz Azofeifa, a structural and seismic engineer with over 45 years of professional experience in structural design, seismic vulnerability assessment, and the rehabilitation and building and infrastructure. Dr. Cruz holds a PhD in structural engineering from the Central University of Venezuela and has led his consulting firm since 1998. Throughout his distinguished career, he has been involved in the design, inspection, and seismic retrofitting of major hospitals, high-rise residential buildings, bridges, heritage structures, and water infrastructure across Latin America. He has served as a technical advisor to international organizations such as the Pan American Health Organization, the World Health Organization, UNESCO, and the International American Development Bank. He is also a former professor at the University of Costa Rica, where he taught structural dynamics, nonlinear analysis, and seismic resistant design. His work has made significant contributions to national building codes and resilience standards in the Costa Rica and across the region. Dr. Cruz, it's a great honor to have you with us today. The floor is yours. Thanks.
Thank you very much for this kind invitation. The Worldwide Council of Civil Engineers have invited us to present the advances and development of the Model Seismic Code for Latin America and the Caribbean. It's an honor for me to present this to this audience, and also for all the members of the code. It's a real honor to transmit these ideas to you. Our history all began in Venezuela in 2013 in the University Central de Caracas, but it was a meeting that did not have success. The real first meeting happened in Santiago de Chile, 2017, November, and was led by the Chilean Institute of Construction. We have there an executive committee who is led by Rodolfo Saragoni. He's a very well-known scholar in structural and earthquake engineering. Myself, the first vice president, Miguel Cruz from Costa Rica. I am leading now the Seismic Code Commission for this country. And also the second vice president, Hector O'Reilly, he's from Dominican Republic. He's running also the Commission for Seismic Code in Santo Domingo. He's also part of the Dominican Republic Association for Earthquake and Structural Engineering. We are supported and aided by a Secretary General, Rodrigo Narváez. He's an architect. He is in Chile. He's part of the Instituto Chileno de la Construcción, National Institute of Construction. We have many members from all the countries in Latin America. Well, maybe not all, but so many. Bolivia, Chile, Colombia, Costa Rica, Cuba, Ecuador, El Salvador, Guatemala, Haiti, Mexico, Nicaragua, Panama, Paraguay, Peru, Dominican Republic, and Venezuela. Many of our members are institutions. For example, the Chicina Association for Earthquake Engineering and Structural Engineering in Chile, AGIES, from Guatemala, ACIES, or from Costa Rica, the Seismic Code Commission in Costa Rica also, Solo Sísmica in Santo Domingo, the Association for Earthquake and Structural Engineering in Santo Domingo, and many others. We are proud to have them as part of our commission, and we are working to obtain finally a code that will be a guide for all our codes. We have an internal organization. We have 4 committees that are working constantly. The first one is the Seismic Hazard Committee that is dealing with the seismic hazard and the seismic demand. We have developed a seismic regional map. We have done also a site classification for soils, and we are proposing a design spectra based on the current systems. This committee is working with a map that will be presented later on. We have also a philosophical committee which leads with the basis for design, analysis methodologies, performance objectives, and many other requirements for the design of structures. We have a housing committee that is dealing with the political and territorial politics that wants to be considered, and also we are supporting this committee with technical support for the design of housing. Another committee is the editorial board committee, which compiled the results of all the others committee to produce only one document that is under writing at this moment. We have not finished the document. We are expecting to have it finished for the next year in a meeting that we are going to have in Santiago de Chile, 10 years after the beginning. What is our purpose? Our purpose is to write basics for a seismic code in order to be used in countries in Latin America as a reference to adjust their code and common formats. We want that we all use the same language and have the same formats for our procedures of seismic design. To promote the technical agreement among the participant countries in order to achieve equivalent performance and seismic security levels using common technical approaches that can be proven with evidence and real results after earthquakes. We write a minimum requirements to be used in the design of infrastructure which will be subjected to earthquake events. At this moment, we are dealing only with building infrastructure. In the future, we want to expand our scope of this code. We want also to establish the criteria for the evaluation and retrofitting of existing buildings, classify buildings according to the importance and expected performance, as we see later on, determine the levels of seismic shaking and demands, that means determine the intensity of the earthquake that we will use to design, and the requirements for geotechnical and structural analysis, as well as the verification of performance of the final structure designed. Which are our guiding principles? The collaboration and solidarity among participant countries. We are working all together to obtain a document that will be good for all of us. Calibration of methodology of local hazard and risk in each country. That's why we are proposing a seismic hazard map for all the Latin America area. Compatibility of the different chapters of the CMS between materials, analysis, and requirements in different kind of facilities. As I said before, we are dealing only with buildings till now. In the future, we want to expand our scope. But the thing is, we have to consider the design very joint in common with the analysis. The analysis and the design is only one part. We cannot think that we make an analysis by one part and the design by others. They will be all together in only one document. The justification of the analysis and design procedure is one of the things we want to propose. What are our technical achievements till now? Till now, we have determined a seismic hazard demand map. We also have proposed methodologies for analysis and design of structures. We also have proposed procedures for design of elements and joints. The methods for foundation analysis and design is under revision and under writing. We have to finish this part, but we are dealing with to finish for the end document. Other technical achievements, we have written soil structure interaction procedures. This is a very good proposal according to the later advances in the area based on the period of vibration of the soil deposits. We have made suggestions about instrumentation of structures. We also have proposed vibration, isolation, and energy dissipation procedures. It is these two things are written in only in one chapter, especially for these kind of issues. We have proposed methods for retrofitting of existing buildings. This also is a very important part of our code. The seismic hazard maps that we have present in our code are maps for rock sites, and they are written for two return periods: 475 years return period and 2,475 years of return period. The map is divided in three parts: the north part of Latin America, the central part of South America, and the south part of Latin America. This map was performed in Seismic by Zenón Aguilar and Juan Carlos Tarazona, helped by Francisco Medina from Chile. The data to obtain this map was given by GEM, Global Earthquake Management, from Padua. Mark Wagani gave us those data, and we proceed to obtain these maps, which are given to us in rock size for two returns periods, as I said before. We also propose a building classification. We have building classification according to importance, regularity, materials, and structural type. Building classification according to importance, it is the buildings are classified according to the lifespan and utility for the society after and during the emergency. For example, temporary buildings are short span life buildings. Normal buildings are the buildings that we usually build to have office, housing, industrial, the common buildings that we always build. Special buildings like data centers, jails, and others, and essential buildings. Essential buildings are the ones for the assistance during the emergency. For example, hospitals or fire departments, station, or emergency offices or centers. For each one of these categories, we propose an importance coefficient I, which is dealing with the intensity that we use to design the building. For example, in normal building, we use a coefficient of 1. That means we are working with the basic earthquake intensity. That means 475 years of return period. But for essential buildings, we use an importance coefficient of 1.5. That has to be with the maximum credible earthquake of 2,475 years of return period. Using this coefficient, we modify the return period for the intensity of the analysis. Building classification for irregularities are considered. We have vertical irregularities classified in the code as well as horizontal irregularities. As you know, the irregularities may present different responses in the buildings, and therefore the design spectra, the reduction factor, the activity, and others details of the design has been considered to calculate the forces of design. That means regularity are very important to that decision about forces. The building classification about materials, we have reinforced concrete, structural steel, masonry, wood, and others. And others, we are having the possibility that the designer may present new materials or potential materials. We also want to avoid the non-ductile behavior of the structure we obtain at the end of the design. This classification is not common in many codes, but we are proposing as an attempt to identify the differences between the material that we use to build the structure. Classification according to structural type. As we all know, we have ductile frames, which are very flexible systems, and also ductile according to the detail we use for reinforce our elements. We also have dual systems. Dual systems combine the ductile frames and the shear walls, and they have a different behavior from the ductile frames. And also, we propose the shear wall systems, buildings that take forces, especially, or earthquake forces, especially by the shear wall effect. They are more rigid than the other ones, and they present different behavior, especially at the base of the shear wall and at the border elements of the shear wall. We also propose to have brace frames, elements, structures that have braces that take the shear forces, especially with axial forces in those brace frames. To determine the seismic shaking level for design, we propose different intensities for design. For example, the basic intensity for design is the intensity that occurs at the side of the building every 475 years as with return period. That means 10% of probability of accidents in 50 years. This is the basic intensity for design. We also may have a maximum credible earthquake intensity. That means 2,475 years of return period that it is used for the design of essential buildings. The difference between these two is as a factor of 1.5. That means that if we want to obtain the intensity for this maximum credible earthquake beginning from the strong earthquake, just multiply by 1.5. This maximum credible earthquake has a probability of accidents in 50 years only of 2%. The performance objectives are as presented. For example, we want to have operational performance with no damage at all. We want to have this operational performance with current earthquakes. The immediate occupancy performance level, we are expecting to have only light damage in our structure. The security of life safety, we are expecting to have moderate damage in our earthquake, in our structure. That means that the life is safe, the building may be evacuated or repaired afterwards. And the collapse prevention is a limit of severe damage, but we want to avoid at all the collapse. These are the goals of the performance objectives. For example, if we look at the yellow squares, we may see that for a strong earthquake, 475 years, we expect to have moderate or less damage in our normal buildings, which are the yellow ones. But for example, in the essential buildings, for that same strong earthquake, we want to have light damage. That means the essential building may continue in service after the emergency of the earthquake. Obviously, in the case of the severe damage for the yellow building, we want to have collapse prevention. Is the severe quite right at the bottom. If we have essential buildings and subjected to maximum considered earthquake, we want to have slight safety in that building. The probability is very, very low, 2% in 50 years. The site classification include the soil characteristics and the modification the soil may do to the signal that apply in the basement of the building has been done based on the velocity, the shear velocity of the excuse me, of the velocity of the shear wave of the first 30 meters in the surface. The velocity of the shear wave of those 30 meters in the surface is proposed in those levels to obtain the different categories of soil characteristics. For example, the fairly dense soil has a velocity, a shear velocity, more than 180 meters per second in a period obtained by the methods of Tanaka of 1.0. This proposal was done by Ramon Verdugo, Simón Aguilar, and Francisco Medina, and they have adjusted this table from the latest developments and advances in the area. With this data, we may obtain the FA and FS coefficients that are later used to calculate the modification of the spectra. And so in the spectra obtained in rock analysis with the map may be modified by FA and FS to calculate the effects of the soil in our spectra. Our spectra is obtained with 3 points, which is given in the map. As I said, well, I did not say before, but in the map, we present 3 maps for each return period and for each area. The 3 maps are the PGA data, the short period spectra, and the long period spectra. And with those short period, long period, and PGA, we may draw this design spectra and afterwards calculate the FA and FS for soil effects. The R reduction factors then are applied. The spectra R reduction factor are based on ductility and over strength. We are still working in these aspects to be proposed in our code. We have not finished yet because many of our countries use different approaches and different focus to perform these reductions. With these reductions and amplifications, we then obtain a design spectra and is defined to calculate then the seismic forces and the displacements. Once we have the structural internal forces due to earthquake and other internal forces, we use the LRDF procedure, that means ultimate load, to calculate the design internal forces of each element. And according to these combinations that are proposed in the code, we design and give size to our elements. We also propose the acceleration records for time history analysis. We want to have real records that properly consider the properties of the seismic sources, magnitude, fault type, and epicentral distance, soil classification, and topography for the site of the project. To do that, we may have basic records for smaller magnitudes or bigger, can be, that may be later modified to obtain our required acceleration record. Also, we are proposing having artificial records, but this is one thing that we have discussed in the future because they are not trustful. Then with all this, we then use the time history analysis of the building. That means elastic or linear or non-linear. We propose also to have linear earthquake analysis method. As you know, we also propose the static method, which is based on a linear mode, in the linear phase mode with a calculated period. We also have model spectral method, which is well known with a combination of a response to each model. Also the time history analysis for the linear procedures. Then this all these things may be modified later with the R, with the R, with the R. Well, it's already done in our spectrum. For the nonlinear, we propose this nonlinear for performance-based design. We also consider the static nonlinear, which is a well-known pushover method, which deal with a lateral load that push the structure till the failure or till the performance point. And also, obviously, we have the time history analysis that consider all the nonlinear characteristics of the elements, and so that we may have a response considering the nonlinear behavior of the house structures. We are proposing simplified methods for housings of 1 or 2 stories. We propose also the soil structure interaction characteristics of the foundation and the soil that support the foundation. As you know, the soil structure interaction modify the response of the structure. We also propose to have isolated structures with special devices at the bottom of the building, so that we may include this to modify the response and have a lighter structure. The soil structure interaction, as you know, consider the flexibility of the soil, and we may model those flexibility of the model with springs and dashpots, so that we may have an increased displacement, an increase of period, but a reduction of forces. We made to revise to check all this data when we make the design to see that the overall stability of the building is attained and the displacement are under control. This analysis we are proposing to have with different characteristics of soil. That means, say, a sensibility analysis of the problem. The analysis procedure for earthquake isolation is based on the introduction of special devices at the base. You know that when you put those devices at the base, then we may have rubber bearing or friction pendulum systems that may modify the overall response of the structure. The principal displacement will happen at the base, and the elements at the base should be good enough to support those displacement. The forces and the displacement or the relative displacement in the upper structure will be reduced considerably. The design procedures that we have are force-based procedure using design spectra. We have not given the step to make a displacement-based procedure. And we use the LRFD, that means load and resistance factor design. Then after that, we also propose to have the performance-based design based on nonlinear analysis. It can be done with pushover or with time history analysis, considering the nonlinear characteristics of the elements. We also are proposing minimum requirements for non-structural systems. It is a very important issue during the analysis, because the non-structural system, that means architectural, mechanical, or electrical, may modify or put the building out of service in an earthquake, during an earthquake. We also proposing the building instrumentations. Our performance-based design requires that we select performance objectives. Then we perform a preliminary design. And with that preliminary design, we make a check or the verification of the performance objectives. If we comply the performance objective, then our design is okay. And we may finish and go on with the drawings and then with the construction. But if no, we need to check the design, modify our elements, modify our details, and do again another verification. If it is okay, then we modify plans and do the things. I want to thank you very much for your attention. This is the Seismic Code for Latin America and the Caribbean, We expect to have this finished for the next year in the meeting that we are going to have in Chile. Till now we have had 8 meetings from Chile, Costa Rica, Panama, Guatemala, Dominicana, Colombia, and El Salvador. The next meeting will take place here in Costa Rica next July, and at the end, we expect to have the document finished for July 2027. Thank you very much.
Okay, Dr. Cruz, thank you very much for this excellent and insightful presentation and for sharing your knowledge and experience with us. Um, in this moment, we're open for questions if you have. So let me see if we have a question. Please open the Q&A question, please. Okay, no question.
Well, anyway, my email address is this at the bottom of this slide. If you want to comment some details in specific, I am open to receive the comments or questions. And also I am going to give this presentation to the Secretariat of the World Council of Civil Engineers, and then you may consult it as you want. And then my possibility is the possibility of connecting me is here in my cellular, if my mail is written there, so that you may contact me in the time you want.
Okay, we have, let me see, we have a question. Yes, for Andy Williams, we will share the presentation, and Marquis Blanco say thank you. Okay, we have question. So we would also like to thank all participants for joining us today. And please remember to complete the survey, share it in the chat. And we invite you to stay tuned for our upcoming webinars and activities. Thank you again for joining us today, and have a wonderful day.
Thank you very much for your attention.
Thank you, Dr. Cruz.